That in a second. LinkedIn is the worst to go live in. I don't know why. It would not keep the settings, so every time you have to start a new event or whatever it's called. Which is highly inconvenient. Why? It would not keep the settings, so every time you have VJ will be starting developing in a sec. Now streaming to 3 different places just because we can. Just because, do I need my CPU in performance mode? Maybe. But what am I monitoring? Clear. Okay, that works. That's nice. Can you explain the code so far? So far. Yep. Just let it talk for a second.
Sure. Let's break down the key components of your game_logic.js script. Canvas setup. The script starts by setting up a canvas with predefined height and width. This canvas is where the game's graphics, waveforms, scores, etc. will be rendered. It defines several colors for use in the game and retrieves the 2D rendering context, CTX, of the canvas. Various variables are initialized: score, game speed, waveform type, current waveform, etc. These are used to track the state of the game. Waveform drawing function.
Okay. Clear. So I just all the chats are in different places to figure out how to monitor them all. There is nothing that will bring them all into one place, which is unfortunate. But we have to deal with it. Okay, so we're going back to this ECG game. Sorry for the ads. I have to clean it. If I turn it into a video, I have to remember to get rid of the ad, because I don't know if it's copyrighted material or whatever. So this game, I don't know if you tried it out. Please do try it out. Let me know what you think. Now the good thing about synthetic, in this case ECG, is that we can try and make a bot that will play this game. And for that, we can use fuzzy logic or neural networks. So we can kill 2 birds in one stone. We'll start with fuzzy logic. With these waveforms, we'll be looking at the amplitude, frequency, but mainly the number of peaks, top and bottom, so up, negative and positive peaks in the data. There are no comments except good morning. Yeah, good morning. We are like in late, early evening. But obviously it's morning somewhere else, which is great. Because we know there's another day coming here as well. Sorry, that's just silly jokes. Right, so we have obviously the code for this application. It's mainly in JavaScript. It's trying to, and we couldn't find a good fuzzy logic library in JavaScript. So I'll have to keep using, I don't know what that is. I have to keep using the Python one. So it's called, yeah, I don't need it, I'll close that. It's called ASCII, because it's using scikit. It's called SK Fuzzy. That's the one we're using. And you can design your fuzzy logic algorithm for your fuzzy sets, fuzzy rules, and defuzzify your signal, which is essentially means in machine learning language that would mean detection, so what's called labeling of the waveforms or whatever you're looking at. So I'll be trying to be doing that quickly. So try running this code. So we created a new folder that eventually will be a new does this code make any backend calls? Any, oh, what's it called? Yeah, backend calls. No, it doesn't.
No,
okay, that's
the game_logic JS script you provided does not make any backend calls. It's a front-end JavaScript code designed to run in the browser. It handles canvas rendering, game logic, and user interactions entirely on the client side. Backend calls typically involve using AJAX, asynchronous JavaScript, and XML, fetch API.
Okay. Can you fix the folders? Yep. Don't need to say yep. Right.
To assist you with organizing or fixing your folders, I would need more specific information about what you're trying to achieve. Are you looking to restructure your project directory, rename folders, or organize your files in a certain way? Please provide more details about the folder structure you currently have and what changes or fixes you want to make. This will help me give you more targeted advice.
That's okay, I wasn't talking to you, I was talking to GitHub Copilot. Yep. That will really get confused.
Got it. If you have any other questions or need assistance with something else, feel free to ask. I'm here to help.
Are there any good fuzzy logic JavaScript libraries? Yep.
Yes, there are several JavaScript libraries that can be used for implementing fuzzy logic. However, the availability and popularity of such libraries may vary, as fuzzy logic is a specialized area. Here are a few options you might consider. Fuzzy Set.js. This is a simple and easy to use library for fuzzy string matching. It's more focused on matching strings with varying degrees of similarity rather than full-scale fuzzy logic operations, but it can be useful in applications where fuzzy matching of text is required. Brain.js. While primarily a neural network library, Brain.js can be adapted for some fuzzy logic applications, especially those involving pattern recognition and decision-making processes. JFuzzy Logic. JFuzzy Logic is actually a Java library, but it's one of the more comprehensive fuzzy logic libraries available. You can use it via JavaScript with the help of WebAssembly or similar tools that allow Java to be run in a web environment. Fuzzy Logic, a simple NPM package that allows you to create a fuzzy logic system. It's more basic but can be a good starting point for simpler applications. Pilot, an interesting project that can be used to create a full application including fuzzy logic. It's more of a full development environment but includes capabilities for fuzzy logic. Remember, the choice of a library should depend on your specific requirements, like the complexity of the fuzzy logic you need to implement, performance considerations, and how well the library integrates with your existing codebase. If none of these libraries meet your needs, you might consider implementing your own fuzzy logic functions. Fuzzy logic algorithms can be written in pure JavaScript, though this requires a good understanding of the underlying principles of fuzzy logic.
Okay, how about Brain.js? How easy it is? It's good that it has a neural network library, but how easy it is to create fuzzy logic with it? Yep.
Brain.js is primarily a neural network library for JavaScript, and is known for being quite user-friendly, especially for those who are new to neural networks or machine learning in general. However, it's important to note that while neural networks and fuzzy logic both fall under the broad umbrella of artificial intelligence, they're fundamentally different in their approaches and applications. Ease of use. Brain.js is designed to be straightforward and easy to use. It offers a high-level API for building and training neural networks, making it accessible even for beginners. Fuzzy logic deals with reasoning that is approximate rather than fixed and exact. It's often used for handling uncertain or imprecise information and for decision-making processes in systems where a clear binary decision is not possible. Neural networks, on the other hand, are a form of machine learning that involves training algorithms on a set of data to make predictions or recognize patterns. They're typically used for tasks like classification, regression, and pattern recognition. While Brain.js doesn't provide direct support for fuzzy logic, you can approximate some aspects of fuzzy logic using neural networks. For example, you can train a neural network to mimic certain fuzzy logic operations or decision-making processes. This would involve preparing your data to represent the fuzzy logic rules and training the neural network to learn these patterns. However, this approach is more a workaround and won't provide the full range of capabilities or the interpretability of a true fuzzy logic system.
Okay. Yeah, Brain.js doesn't sound a good solution. We might use it later for doing the same detector in using neural networks. But currently we would like to design a fuzzy logic system that will play the CardioQuest ECG waveform detection game. Using JavaScript would be great. If not, we could have a Python backend and turn this into a Flask application. Any thoughts? Yep.
Designing a fuzzy logic system for your ECG waveform detection game can be approached in two main ways, using JavaScript for a client-side implementation, or integrating a Python backend, like a Flask application, for more complex computations. Here's an overview of both approaches. If there aren't any specific fuzzy logic libraries in JavaScript that suit your needs, you can implement the fuzzy logic system from scratch. This would involve defining fuzzy sets, membership functions, and the rules for inference. You need to be mindful of performance implications, especially if the fuzzy logic computations are complex. Python has a more extensive range of libraries for fuzzy logic, like scikit-fuzzy. These libraries offer more functionality and are generally well documented and supported. Python's libraries are more mature for this kind of computation, potentially saving you time and providing more robust functionality. Offloading the computation to the back end can be beneficial from a performance standpoint, especially for complex calculations. This approach
Okay,
introduces more...
Okay, you convinced me. Let's go with a backend. So essentially we're making a Flask application that will have the fuzzy logic detector running on the back end. We would like to extract features from the waveform. We would like to extract 3 features: frequency, amplitude, and the number of positive and negative peaks in the waveform. Yep.
Creating a Flask application with a backend capable of extracting features from an ECG waveform is a great approach. Here's a high-level overview of how you can set this up, focusing on extracting frequency, amplitude, and the number of positive and negative peaks. Flask application, set. Create a REST API endpoint in Flask that accepts waveform data, possibly as a JSON payload, and returns the extracted features. Frequency analysis, use. Use fast Fourier transform, FFT, to analyze the frequency components of the waveform. Libraries like NumPy or SciPy are excellent for this purpose. Extract the dominant frequency or a range of frequencies that are of interest. Amplitude analysis. Determine the peak-to-peak amplitude of the waveform. This can be done by identifying the maximum and minimum points of the waveform and calculating the difference. Peaks detection. Utilize signal processing tools from SciPy or similar libraries to identify peaks. Count the number of positive and negative peaks. Positive peaks are usually the local maxima, while negative peaks are local minima. Data transmission, your front end. Your front end, JavaScript, will send the ECG waveform data to the Flask backend using AJAX, Fetch API, or similar methods. Once the Flask backend processes the data, it will send back the extracted features, frequency, amplitude, and peaks count, to the front end. The front end can then display or use these results as needed. Testing. Initially, test your feature extraction algorithms with a known dataset to ensure accuracy. Scalability. Ensure your Flask server can handle the expected load. If the processing is heavy, consider asynchronous processing or queuing mechanisms. Security. Implement necessary security measures for data transmission, especially if handling sensitive biomedical data. By following this structure, you can create a robust system that leverages the power of Python's data processing capabilities on the back end, with a responsive and interactive front end.
Ooh. Can you remind me the structure, folder library, a folder structure for a Flask application? Flask application. Yep.
Certainly. Here's a typical folder structure for a Flask application. This structure helps in organizing your code and resources in a manageable and scalable way. App, main application directory. Asterisk. Static, contains all static files like CSS, JavaScript,
Can we do a simplified version of it? Yep.
Absolutely. For a simplified Flask application, especially for smaller projects or prototypes, you can use a more streamlined structure. Here's a basic layout. Static. This directory will hold all static files such as CSS.
Do we really need the CSS and JS folders, separate folders? Can they just be within the static folder? Yep.
Yes, you can definitely keep your CSS and JavaScript files directly in the static folder without creating separate subfolders for them. This approach simplifies the structure further, especially for smaller applications or when you have only a few static files. Here's how your modified structure would look. In this setup, static directly contains your CSS and JavaScript files, _style. Style.css, your CSS file. Templates, as before, this folder contains your HTML templates. Index, HTML, main HTML file for your application. App.py, the main Flask application file. Requirements.txt, lists your Python dependencies. When using static files in your HTML,
Okay. Wanna try something out quickly. Mainly because so we tried using the workspace feature in GitHub Copilot that's supposed to answer questions about all the open files, well, in Visual Studio Code that are currently open. In theory, if you ask about the file structure, it's collecting workspace structure, deciding which workspace information to collect, collecting workspace info, and giving me an array buffer allocation failed error. And what I want to try is open a new window of Visual Studio Code. Just try it out. Open folder. So say this port. Right now. A workspace file structure. Collecting workspace structure, collecting info. Right, and it's actually seemed to work, which is good. So if we do workspace again, can we turn it into a Flask application? Let's see if it's actually can do more general tasks. Yes, you can create it. Okay. You're not gonna do it for me, do you? Are you? Okay. Can you actually do this for me? I don't know why it's collecting code. Right, this is interesting. So it's unable to make files and things. Because it's surely again workspace. Can you generate the terminal commands to change the file and folder? Yeah, it keeps sending it too quickly. That's okay. So why it's collecting code. Right. Can run it in. Don't need to show ports. Is static. Yep, obviously that worked. I don't know why it couldn't just do it itself. Move these files. Okay. To move the files. We already have Flask installed. How does this generates, right, so from terminal essentially can write code. Okay, that can make sense. So there is a Flask application there. That's great. Okay, back to the fuzzy logic stuff. Which library are you recommending to use so we can quickly use the fuzzy logic system to play the ECG detection, abnormal ECG detection game? Yep. Let's see what that one says.
For implementing fuzzy logic in a Python-based backend, like Flask, I recommend using the scikit-fuzzy library. It's a robust and easy-to-use library for fuzzy logic algorithms and is built on top of NumPy, SciPy, and Network X, which makes it quite powerful for scientific computations. Here's why scikit-fuzzy is a good choice for your project. Comprehensive toolkit. It provides a wide range of tools for creating and manipulating fuzzy sets and systems, which is essential for any fuzzy logic-based application. Ease of use. Despite its comprehensive feature set, scikit-fuzzy is user-friendly, especially if you're already familiar with Python's scientific stack. Well documented. The library is well documented, which is beneficial for quick learning and reference. Community and support. Built on widely used Python scientific libraries, it benefits from a strong community and support. Installation. You can easily install scikit-fuzzy using pip, bash copycode pip install scikit-fuzzy. Integration with Flask. In your Flask application, you'd use scikit-fuzzy to analyze the ECG waveform data received from your front end and apply fuzzy logic rules to detect abnormalities. Feature extraction and analysis. For your specific requirement of analyzing frequency, amplitude, and peaks, you'd integrate scikit-fuzzy with other Python libraries like NumPy or SciPy. NumPy can help with general numerical calculations, while SciPy is great for signal processing tasks. Receiving data. The front end sends ECG waveform data to your Flask backend. Processing data. Use SciPy for initial processing, like FFT for frequency analysis, peak detection, etc. Fuzzy logic analysis. With the processed data, utilize scikit-fuzzy to apply fuzzy logic rules and determine the presence of abnormalities. Sending results back. The Flask backend then sends the analysis results back to the front end for display or further action. Scikit-fuzzy is ideal for a project like yours where you need to make nuanced decisions based on imprecise or variable data, typical in ECG waveform analysis. It allows for the flexibility and depth required for such applications while being accessible and practical for rapid development.
It'll be interesting to see if GitHub Copilot can do those things all at once. Just sit back, relax, it will be coding for you. So I think I need to select the workspace. So obviously it's not only taking files that are currently open, but everything, in the workspace. So that's okay. So let's see what it says if we just pop all of it in. Sorry for that. Why does it say enable? It's actually started doing stuff. So currently we just have the game running. No, it's not running anymore. Of course not. We broke it. Well, one thing, it's now not going to be HTML anymore. Now you need to actually run the Python code. For it to work. Well, it doesn't. Getting all these errors. Need to fix the folders in HTML. Do we? I think so. In HTML. Don't know why it wasn't able to access the file. Is it still, yeah, looking for it in the wrong place? How do we regenerate that response? A workspace. Check the file structure again. It changed. So it should know, but go figure. So I'm pretty sure it would not work from the HTML anymore because now it's a Flask application. Yeah, we updated the workspace. That's right. Let's try workspace that again. Okay, now think, do we need to normalize frequency, amplitude, and peaks metrics from 0 to 1 so the membership functions and fuzzy rules work okay, or better, or work at all? Yep.
Yes, normalizing your data, including frequency, amplitude, and peaks, to a range from 0 to 1 can be very beneficial when working with fuzzy logic, especially when using membership functions and fuzzy rules. Here's why normalization is important and how it helps. Consistency across features. Normalization brings different features, frequency, amplitude, peaks, onto the same scale. This is crucial when these features have different units or scales of measurement. Effective membership function mapping. Fuzzy logic often relies on membership functions to classify inputs into linguistic variables, like low, medium, high. Normalized data ensures that these membership functions can be applied consistently and meaningfully. Simplified rule creation. When working with normalized data, creating fuzzy rules becomes more intuitive. You can define rules based on the normalized range, 0 to 1, which is often easier to conceptualize and implement. Improved algorithm performance. Normalized data can lead to more stable and reliable fuzzy inference, as the algorithms work best when all input features are within a similar range. Normalization typically involves transforming data so that it fits within a specific scale, like 0 to 1. A common method for this is min-max normalization. Determine ranges. First, determine the range of values for each feature, frequency, amplitude, peaks, in your dataset. Normalize data. Apply normalization to each feature before feeding them into your fuzzy logic system. Design membership functions. Create membership functions based on the normalized range. For example, you might define low, medium, and high categories within the 0 to 1 range. Define fuzzy rules. Create fuzzy rules that operate on these normalized and categorized values. Normalization is not just a beneficial step, but often a necessary one in fuzzy logic systems for ensuring that the inputs to the system are consistent and that the membership functions and rules work effectively. It makes the implementation of fuzzy logic more robust and the results more reliable.
Okay, don't know why the double thing anymore over there. We are not in GJS, are we? Why are you so silly? Right, that's working. Silly robot. Okay, we need to function to normalize the waveforms. No. I don't know how this works. So if we have another, obviously we need all that. So all this stuff goes in here. From Flask we can also import request. So we can close that. And data is not being accessed. Okay. Pretty sure we have SciPy installed. And we have a process data, some function. Okay. The fuzzy logic. It should be as fuzz or something. Yeah, maybe to leave it as is. I don't understand this, like importing as something else. It's kind of silly. Well, that's also because I don't know Python. Likely we have ChatGPT or GitHub Copilot. Okay, we have some functions sending results back. So we have the upload data post, receive data. A process data. Okay, this will obviously not work. Let's clear this out. Do we have the calls? No. Okay, so when will the bot do detection or anything? Right, obviously the index HTML, if you just open live server, How does that even works? That's interesting. I'll keep them both open, the different ports, just testing locally. I was silly enough to think if we have the Flask application running, then the HTML by itself will not work anymore. So obviously I was wrong. I was wrong. The main thing is this application now. So we're using fuzzy logic toolbox, using SciPy, some function. Okay, now it's a tricky business. Now we need to normalize as well. We'll keep that prompt there. We have a template for the Python script. That looks like this. Can you continue providing GitHub Copilot prompts as per previous discussion? Yep.
Certainly. Continuing from where we left off, let's expand on the Python script template you've provided. This script integrates Flask for the web server, SciPy for signal processing, and scikit-fuzzy, imported as skfuzzy, for fuzzy logic analysis. The structure is a great starting point for your ECG waveform detection game. I'll add some more details to the process_data and analyze_data functions, keeping in mind the requirements of extracting frequency, amplitude, and peaks, and then applying fuzzy logic analysis. Process_data function, this function applies signal processing techniques to the input data. For example, using FFT for frequency analysis and Skippy's find out.
I like how it didn't trust GitHub Copilot and started generating the code itself. Just fair enough, I trusted a bit more than GitHub Copilot anyway. To finish that
this template serves as a starting point. You'll need to adjust and expand it based on the specific details of your ECG data and the requirements of your game.
Clear. Can you explain why you chose streamF instead of the trapezoidal membership functions? Yep.
The choice between triangular, TRIMF, and trapezoidal, TRAP-MF, membership functions in fuzzy logic often depends on the specific requirements of the application and the nature of the data being modeled. Here's why I initially chose the triangular membership function in the example. Simplicity. Triangular membership functions are straightforward and easy to implement. They're defined by just 3 points, start, peak, and end, making them less complex to configure compared to trapezoidal functions. Suitable for unclear boundaries. When the precise boundaries of a category are not clear or when there's a gradual transition between categories, triangular functions can be a good fit. Generalization. For many applications, especially in initial designs or prototypes, the triangular function is a good starting point due to its simplicity and general applicability. Performance. In some cases, simpler membership functions like triangular ones can lead to faster computation, which might be beneficial in real-time applications. Better for defined ranges. Trapezoidal functions are more suitable when you have a clear understanding of the range over which a variable should be considered fully part of a set. This is due to the flat top of the trapezoidal function, which represents a range where the membership degree is constant and maximum. Flexibility. They offer more flexibility in defining membership functions as they involve 4 points: start, upper end, and end. This allows for a more nuanced representation of fuzzy sets. Data and context understanding. If you have a deep understanding of your data and the context, and if there are clear plateaus where a variable should fully belong to a set, TrapMF might be more suitable. Experimentation and refinement. You can start with TRIM for its simplicity and then experiment with TrapMF to see if it offers more accuracy or better reflects the real-world scenarios you're modeling. In the context of ECG waveform analysis, starting with TRIMF is a practical approach, especially in the early stages of development. As you refine your model and gain more insights into how your variables behave, you might consider switching to or experimenting with TrapMF. The decision should be guided by the behavior of your data and the specific requirements of your fuzzy logic system.
Okay, one thing I do not understand so with workspace, is the Python script being used at all? We just added it. Do we need to adjust any of the JavaScript files? It's particularly the game logic file. It says it is being used. Game logic is in a different folder now. Should know that. Also the waveforms is okay, but the game logic, is this file referring to the Python Flask application functions? It is not. How can I integrate the JavaScript game logic with the Python Flask application? So there are Ajax requests talking between them. I don't want to show the score. Okay, is it possible to treat the backend as the expert? So it will only have fuzzy logic and will only get the waveforms and nothing else. The score will be hidden from it. And on the HTML page, we will show both the score that coming from the JavaScript and the model result that is coming from the backend. But we want to make sure they are independent. 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 Oh, come on. Yep. 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 Let's see if it understands the context or not.
Yes, it's entirely possible to set up your Flask backend as a dedicated, expert system for fuzzy logic analysis, with the front end, HTML, JavaScript, handling the scoring and display of results independently. Here's how you can structure this. Focused role: the Flask backend will exclusively receive the waveform data, apply fuzzy logic analysis, and return the analysis results. It won't handle scoring or other game logic. Endpoint for analysis: create a specific endpoint in your Flask app that receives waveform data, processes it through the fuzzy logic system, and returns the analysis result. Example endpoint in Flask. Handling scores: implement the scoring logic entirely in your JavaScript code. The score will be calculated based on user interactions and game rules defined on the client side. Displaying results: use AJAX or Fetch API to send waveform data to the Flask backend and receive the analysis result. Display this result on your HTML page. Updating and displaying the score. Sending waveform data to the backend for analysis and displaying the returned results. Asynchronous calls: make asynchronous calls from your JavaScript to the Flask backend. This way, the game's flow isn't interrupted while waiting for the analysis results. Separate display elements. On your HTML page, have separate elements for the score and the model results. For instance, use different divs or sections to display this information. By separating the concerns, back-end for fuzzy logic analysis and front-end for game logic and scoring, you create a more modular, maintainable, and scalable application. This approach allows each part of your application to focus on its specific tasks without interference, leading to cleaner code and potentially smoother user experiences.
What's the file structure of the application? Can you generate a quick diagram out of it? Yeah, it's not like talking to the thing. Yeah, it's getting confused. It's getting confused. Let's try again. Workspace. Generate a clear diagram of the file and folder structure of this application. Let's just look at the workspace. Generate one of those. Yeah, that's the one. I have the following structures. I'll start uploading the script in the files in the next prompt. I need your help modifying the files based on our previous discussion. Yep.
Sure, I'd be happy to help you modify the files based on our previous discussion. Please upload the app.py, game_logic, JS, waveforms, JS, and index, HTML files, and let me know the specific modifications and additions you need for each file. This might include integrating the fuzzy logic analysis in the Flask app, updating the JavaScript for game logic and scoring, or modifying the HTML for displaying results. Once I have the files and your specific requirements, I can provide more targeted assistance.
Okay. App by is exactly the same as what you suggested in the earlier prompt. I need help integrating the changes as discussed in a previous conversation. Earlier. Yep.
Based on our previous discussion and the files you've provided, we'll make modifications to integrate the fuzzy logic analysis from the Flask backend, app.py, into the game logic in game_logic, JS, and display the results on index, HTML. Here's a breakdown of the changes. You'll need to add functionality to send waveform data to the Flask backend for fuzzy logic analysis and then handle the response. Add function to send data to Flask backend, this. Create a function to display the analysis result from the backend on the web page. Call analyze waveform function whenever a new waveform is generated in the game loop. Add an element in index, HTML to display the analysis result from the backend. Place this element where you'd like the analysis results to be displayed on the page. Make sure app.py contains the analyze_waveform endpoint, as discussed previously, to receive waveform data, process it with fuzzy logic, and return the result. With these changes, game_logic, JS will send the current waveform data to the Flask backend for analysis. The backend applies fuzzy logic and returns the result, which is then displayed on the web page. This integration allows the Flask backend to act as an expert system for waveform analysis, while the front end handles the game logic and display independently. Remember to test the integration thoroughly to ensure that the data is correctly sent, processed, and received, and that the game's flow remains smooth and responsive.
List all the functions. not actually giving me code for that. I'll try to get the Copilot to do it. Changing the code quite a bit. Don't like it. Can you explain? How do I use the function?
To call the analyze waveform function whenever a new waveform is generated in your game loop, you should place the function call right after a new waveform is created and set as the current waveform. In your game_logic.js, this would typically happen in the game loop, specifically in the section where you check if the current waveform has completely scrolled off the canvas and generate a new one. Here's how you can integrate it. Locate the waveform generation section, find the part in your game loop where a new waveform is generated. This is usually where you check if the current waveform has scrolled off the canvas. Call analyze waveform after new waveform creation. After you set the new waveform, call analyze waveform with the newly generated waveform data. Here's an example based on your existing code structure. In this snippet, the analyze waveform function is called right after a new waveform, current waveform, is generated. This ensures that each time a new waveform appears on the screen, it gets sent to the Flask backend for analysis. Make sure that the data format sent to analyze waveform matches what your Flask backend expects. For instance, if your backend expects an array of waveform points, ensure the current waveform is formatted accordingly.
We have we're calling the function now. Console log remain the same. Yeah, we're just playing the waveform type. Okay, so that warning went away. Right, we need a display element in index HTML. Can we do this? Just wondering. Should be here somewhere. Oops. Comment that. Analysis result. Oh, that's okay. Make sure apply. Analyze waveform, just analyze. Because we took the Analyze waveform. Just mess up the name, or the endpoint. It's not an endpoint. This is odd. Are we actually calling it somewhere? Yes, we are. We have. I don't even know how the two JavaScripts interact between them. Make sure this ID is actually in the JavaScript. Yes, it is. Do we still need the following function, the following endpoint? Yeah, because two of them, I don't get if they are the same.
In your current setup, based on the discussion and the provided game_logic.js file, you do not need the analyze endpoint in your Flask application, app.py. Instead, you should use the analyze_waveform endpoint, which was specifically designed to handle the waveform data sent from your JavaScript game logic for fuzzy logic analysis. Endpoint in Flask, app.py, you should have an endpoint like analyze_waveform in your Flask app. This endpoint will receive the waveform data, process it using your fuzzy logic system, and return the analysis result. In your JavaScript file, you should have a function like analyze_waveform that sends the waveform data to the analyze_waveform endpoint and handles the response. Here's how the Flask endpoint might look. And in your JavaScript, you call analyze_waveform with the waveform data. By setting up your application this way, you ensure that the game logic in the front end and the fuzzy logic analysis in the back end are properly connected and communicating effectively. Remember to test this integration thoroughly to ensure that the data flow between your front end and back end is functioning as expected.
Yeah, that app by is not right. Can you help me updating the Python code? It's missing the following function. I'm pretty sure I have it already, but it's just called something else. The whole code might need refactoring. Get a timeout for ChatGPT. What is
To
it?
integrate the fuzzy logic analysis into your Flask application, you'll need to ensure that the fuzzy _logic _analysis function is properly defined and connected to your analyze _waveform endpoint. From your provided code, it looks like the fuzzy _logic _analysis function is intended to be the analyze _data function. We can refactor the code to make this connection clearer. Let's update the Flask application to use analyze _data as the fuzzy logic analysis function. I will rename analyze _data to fuzzy _logic _analysis for clarity and ensure it's called correctly in the analyze _waveform endpoint. Renaming analyze _data to fuzzy _logic _analysis, the function analyze _data has been renamed to fuzzy _logic _analysis for clarity. This function now clearly represents the part of your code responsible for applying fuzzy logic to the processed data. Processing data before analysis. In analyze _waveform endpoint, the received waveform data is first processed by process _data and then passed to fuzzy _logic _analysis. This ensures a clear separation of concerns, data preprocessing and fuzzy logic analysis. Ensure that the normalize function is used correctly within fuzzy _logic _analysis to scale input values appropriately. After making these changes, test the application to ensure that the data flow from the front end to the back end works correctly, and the fuzzy logic analysis is performed as expected. Pay attention to how the data is formatted and passed between functions to avoid any mismatches in expected input-output formats. This refactoring should align your Flask application with the intended structure and functionality, making the fuzzy logic analysis part clear and effectively integrated with the rest of your application.
Yeah, we have another problem. The processed data is returning individual components. That should be okay. A fuzzy logic analysis. And normalized. Do we have normalized? No. No, we do. It can be normalized. It's normalizing everything from 0 to 1. That's good. And generate these functions one by one.
The process_data function in your Flask application is responsible for preparing the waveform data before it's analyzed by the fuzzy logic system. This typically involves tasks like signal processing, feature extraction, and normalization. Based on your application's focus on ECG waveforms, let's outline what this function might include. Here, you'll apply techniques like fast Fourier transform, FFT, for frequency analysis and peak detection to extract meaningful features from the ECG data. You might want to extract features like the dominant frequency, the number of peaks, both positive and negative, and the amplitude of the waveform. Normalize these features to a standard range, usually 0 to 1, to ensure consistency and compatibility with the fuzzy logic analysis. Frequency analysis, the FFT is applied to the waveform to get the frequency components. The dominant frequency is extracted for analysis. Peak detection, Skippy's find_peaks function is used to detect peaks in the waveform. The number of peaks is counted. Amplitude calculation, the difference between the maximum and minimum values of the waveform gives the amplitude. Normalization, each extracted feature is normalized to a range between 0 and 1. Data format, ensure that the data format received by process_data matches the format of the waveform data sent from the front end. This function sets the stage for the fuzzy logic analysis by extracting and normalizing the key features from the ECG waveform data. You might need to adjust the implementation details based on the exact nature and format of your ECG data. The fuzzy_logic_analysis function in your Flask application is the core of the fuzzy logic system. It uses the process data to evaluate and classify the ECG waveform based on predefined fuzzy rules. This function should define the fuzzy variables, membership functions, and rules that constitute your fuzzy logic system. Let's outline the implementation of this function based on the process data, which includes normalized frequency, amplitude, and the number of peaks. Fuzzy variables and membership functions. Define fuzzy variables, frequency, amplitude, peaks, and their respective membership functions. Adjust these based on the specifics of your ECG data. Rules. Establish rules that dictate how the inputs relate to the output, abnormality. These rules are based on your understanding of what constitutes an abnormal ECG waveform. Control system. Set up the control system using these rules and then simulate it with the process data. Compute result. Finally, compute the output, which gives the degree of abnormality based on the input waveform data. This function forms the decision-making core of your application, determining the likelihood of abnormalities in ECG waveforms using fuzzy logic. The effectiveness of this system will largely depend on how well the membership functions and rules model the real-world behavior of ECG waveforms. You may need to fine-tune these aspects based on testing and domain expertise.
It is a minor error. Let's see what Copilot says.
The error message you're encountering in game_logic.js suggests that there is an issue with parsing JSON data. This typically happens when the expected JSON data is either not received correctly or is malformed. The error points to line 192 in game_logic.js, which is likely within the analyze waveform function or a similar function where you're handling the response from your Flask backend. To troubleshoot this issue, follow these steps. Ensure that your Flask backend, app.py, is correctly sending a JSON response. The response should be properly formatted as JSON. For example, in your analyze waveform function, make sure you are correctly sending the request and handling the response. Pay attention to how you pass the response. Console log. Add console.log statements to print out the response from the server and any data you receive in the analyze waveform function. This can help you identify where the breakdown is occurring. Check network response. Use your browser's developer tools, usually accessible with F12 or right-click to inspect, then go to the network tab. Check the response from your analyze_waveform call. Ensure that the response is valid JSON. It's good practice to handle cases where the response might be empty or not in the expected format. Ensure your code gracefully handles these scenarios without throwing an error that could break your application's flow. By following these steps, you should be able to identify and resolve the issue causing the unexpected end of JSON input error in your game_logic, JS.
Should be simple for Copilot. Right, that's better. Make sure in JavaScript the function fetching analyze waveform, it's a post method. Line it's the same. Yeah, it's giving that error. Something in the JSON response or format. Still troubleshooting. So we do get that error. Let's try GitHub Copilot.
The error
as
HTTP error. Status 405 indicates that the method used in the HTTP request is not allowed for the URL requested.
well.
In the context of your game_logic, JS, it means the fetch request to your Flask backend is using a method that the Flask root does not support. Since the error is a 405 method not allowed, let's check a few things. Verify that the Flask root is set up to allow the HTTP method you're using in your JavaScript fetch request. For example, if you're using a POST request in JavaScript, ensure your Flask root is configured to accept POST requests. Make sure that the method you specify in the fetch request matches the method allowed in your Flask root. For instance, if your Flask root accepts POST, your fetch should also use POST. If your frontend and backend are served from different origins, different domains, ports, or protocols, you might run into cause issues. Flask roots need to be configured to allow requests from different origins in such cases. You can use Flask cause extension to handle this. Install Flask cause and use it in your app.py. Ensure the URL in the fetch request is correct and corresponds to the route defined in your Flask app. If you're running the Flask app locally, it's usually something like http://localhost port 5000/analyze_waveform.
Okay, there's a problem that we so this should be okay. And JavaScript should be okay as well. A course should be fine, I think. But yes, we're actually not running the Flask application. No, we are, but we are not using the correct you should be using this link. Yeah, right. There are no comments, unfortunately. Or fortunately, that's how you look at it. Analysis result. Get the element by ID. Getting an error in line 201. So analyzing waveform doesn't work. Would this just regenerate the whole function?
Your analyze waveform function in game_logic JS is intended to send the waveform data to your Flask backend, receive the analysis results, and then handle these results, e.g., by displaying them on the page. Here's an example of how you can structure this function. Sending data, the function sends a post request to the analyze_waveform endpoint with the waveform data as JSON. It first checks if the response status is OK, status code 200 to 299. If not, it throws an error. If the response is OK, it passes the JSON response. Displaying results, the parsed data, analysis result, is then passed to display analysis result to update the UE. Error handling, any network errors or issues with the request are caught in the catch block and logged to the console. You need to call analyze waveform at the appropriate moment in your game loop, typically when a new waveform is generated. Make sure the waveform data you pass to the function matches the format expected by your Flask backend. Use console logs to debug and ensure that the data is being sent and received correctly. Check the Flask server logs for any errors or issues on the backend side. Use Browser Developer Tools, Network tab, to inspect the HTTP request and response details. This function plays a crucial role in integrating your front-end game logic with the back-end fuzzy logic analysis. Make sure to test thoroughly to ensure seamless integration.
Right, I actually didn't notice this error in the terminal.
The error you're encountering in your app.py script is due to the way the normalize function is being used. The normalize function expects an iterable, like a list or an array, but it looks like you're passing a single integer value, numpy.int64, to it. The min and max functions are being called on a non-iterable, hence the type error. Let's address this issue. You need to modify the normalize function so it can handle single values correctly. Here's an updated version of the function. In this version, you need to provide the minimum and maximum values of the range from which value originates. This way, the function can handle single integer or float values properly. Modify the calls to the normalize function in the process_data function to include the minimum and maximum values for each feature. Remember to replace the freq_min, freq_max, peaks_min, peaks_max, amp_min, and amp_max values with the actual minimum and maximum values expected for your frequency, peaks, and amplitude data. Normalization. The normalization process adjusts the range of your data to fit between 0 and 1. This is important for consistent fuzzy logic analysis, especially when combining different features. Data ranges. It's crucial to know the range of values your data can take. For example, if you're analyzing ECG waveforms, you should have an idea of the typical range of frequencies, number of peaks, and amplitude values. By making these adjustments, your normalize function should work correctly with the data being processed, and the type error should be resolved.
Don't like it. I don't think it's relevant. Can we regenerate that last response?
The error you're encountering, type error, numpy.in64 feet object is not iterable, is happening because the normalize function is trying to iterate over a single numerical value, numpy.in64. The min and max functions are being called on a non-iterable object, which is causing the issue. This typically occurs when you're passing a single value, like an integer or a float, to a function that expects an iterable, like a list or a numpy array. Let's correct this in the process_data and normalize functions. In process_data, when you're calling normalize, dominant_frequency seems to be a single numerical value rather than an array. You should modify the normalization process to handle single values correctly. Here's a revised version of the normalize function to handle both single values and arrays. And in process_data, you need to adjust how you call normalize. First, determine the range for normalization, i.e., the global minimum and maximum values for frequency, peaks, amplitude, etc., based on your dataset or predefined ranges. Then, use these values when calling normalize. Example adjustment in process_data. Normalization range. It's important to define the range, minimum and maximum values, for each feature based on your specific data or application requirements. This range is used in normalization to ensure consistency. Single value normalization. The revised normalize function now correctly handles single numerical values. By making these changes, you should resolve the type error and ensure that your data is normalized correctly before being passed to the fuzzy logic analysis. Remember to adjust the global minimum and maximum values based on the actual range of your data.
A problem is that I do not know the global minimum and maximum frequencies, or global minimum and maximum peaks, or global minimum maximum amplitude. Yep.
If you do not know the global minimum and maximum values for frequency, peaks, and amplitude, there are a few approaches you can consider. Use your knowledge or literature in the field to estimate reasonable minimum and maximum values for these features. For example, in the context of ECG waveforms, you might know the typical range of frequencies, number of peaks, and amplitudes that are expected. If you have a dataset of ECG waveforms, you can analyze this dataset to determine the range of values for each feature. This can be done by calculating the minimum and maximum values across all your data. If the data comes in a stream and you cannot analyze it in advance, you can implement an adaptive normalization technique. Keep track of the minimum and maximum values encountered so far and use these to normalize new data. For some features, it might make sense to normalize them relative to each other within the same waveform rather than for an absolute range. For example, you can normalize the peaks in a waveform relative to the highest peak in that same waveform. Since you're working with ECG data in real time, a combination of domain knowledge estimation and adaptive normalization might work best. Here's an example of how you might implement adaptive normalization. In this example, global minimum and maximum values for each feature are updated every time new data is processed, allowing the normalization process to adapt to the range of data encountered over time. This approach is dynamic and can handle varying ranges in your data.
No, I do not want the adaptive normalization. Can I get those values from waveforms.js? Or is it contradicting the requirement for the fuzzy logic being independent from the waveform generation? Yep. Well, we know what the answer for that should be.
Retrieving the global minimum and maximum values for frequency, peaks, and amplitude directly from waveforms, JS in a real-time setting could be challenging, especially if you want to keep the physiological analysis independent from waveform generation. However, there are a few strategies you could consider. If you have a sample dataset of ECG waveforms, you can analyze this dataset offline, i.e., before the real-time application runs, to determine the approximate range of values for each feature. This way, you can hardcode these values into your Python script. This approach does not require real-time interaction with waveforms, JS, and maintains independence. If you have domain knowledge about typical ECG waveforms, or can consult literature or experts, you might be able to define reasonable static ranges for these features. These predefined ranges can be used for normalization. Another approach is to calculate and send these ranges from the front end, JavaScript, to the back end, Flask, at the start of the session. However, this approach slightly blurs the line of independence between waveform generation and analysis. It's feasible if the initial calculation in waveforms, JS, does not continuously influence the physiological analysis. If you prefer keeping the back end and front end completely independent, it's better to use a combination of offline analysis and domain knowledge to set these ranges in the back end. Offline analysis. Run a script to process a batch of sample ECG data to find the min and max for frequency, peaks, and amplitude.
Okay, can we go over the adaptive normalization again? Yep.
Certainly. Adaptive normalization dynamically adjusts the range used for normalization based on the data it encounters over time. This approach is particularly useful when dealing with data whose range is not known beforehand or may vary significantly. Let's revisit the adaptive normalization method for your use case. Tracking global min and max. As new data points come in, the algorithm updates the global minimum and maximum values based on these points. This way, the normalization range adapts to the data seen so far. Normalization. Each new data point is then normalized based on the current global minimum and maximum values. Here's how you could implement adaptive normalization in your Flask application for ECG waveform data. Initial values. The global minimums are initialized to float, INF, and the maximums to float, INF, to ensure that any real data point will update these values. Normalization. The normalize function handles the case where the minimum and maximum values are equal, to avoid division by zero. Data range update. Each new piece of data updates the global range. This means that over time, as more data is processed, the normalization range becomes more representative of the actual range of the data. This approach will continuously refine the normalization range as more data is processed, making it more accurate over time. It's a suitable method when dealing with varying data ranges or when predetermined ranges are not available. Just keep in mind that the initial data points might be normalized less accurately until the system has seen enough data to establish a representative range.
Okay, that sounds good. We might need more help integrating it into the current code. Yep.
Absolutely. I'd be happy to guide you through integrating adaptive normalization into your current code. We'll focus on modifying the process_data function to implement adaptive normalization for the frequency, peaks, and amplitude values of your ECG waveforms. First, define global variables in your app.py to keep track of the minimum and maximum values encountered for each feature, frequency, peaks, amplitude. Create a function to update the global minimum and maximum values. In process_data, use the global min and max values to normalize the data and update these values based on the new data. Ensure the normalize function handles single values correctly. Global variables. The global variables store the current minimum and maximum for each feature across all processed data. They are updated each time new data is processed. Normalization. Each feature is normalized based on the current global min and max values. Dynamic adaptation. This setup allows the normalization process to dynamically adapt to the range of data being processed over time. Test this setup with various waveforms to ensure that the normalization process works correctly. Monitor the global min and max values to check if they...
Okay, so we define global variables for minimum and maximum for each of the parameters. We're looking at frequency, amplitude, and peak. And we have now a function that returns minimum and maximum for the current minimum value. Okay. It should return min and max in process data.
In process_data, use the global min and max values to normalize the data and update these values based on the new data.
We have the normalized frequency. To update that. Oops, no. All normalized peaks. A normalization function. A normalize should be somewhere at the bottom. Yeah, avoid division by 0. It's a great idea, great suggestion. And it's started. Okay, how is it still working? How is it still? Okay, what is? So we're not running the correct thing. It should be this one. Yeah, that's right. To actually run the Flask application. Yes, this domain is okay. Is it something we're getting for the first few waves? No, we keep getting it. Analysis result. We get an analysis result. Yeah, that's what I thought. We would not get a value for the... So we had a video freezing. This number, analysis result is always, no, it's always 0.8. Yeah, that one. Yeah, we might keep troubleshooting. I'll say bye-bye for now. Continue next time.
The error you're encountering in your fuzzy logic system, value error, crisp output cannot be calculated, likely because the system is too sparse, suggests that the fuzzy inference system is unable to produce a valid output. This usually occurs when the input values do not sufficiently activate any of the fuzzy rules you defined, leading to an inability to compute a defuzzified, crisp output. Here are some steps to troubleshoot and resolve this issue. Ensure that the input values, frequency, peaks, amplitude, fall within the range expected by the membership functions defined in your fuzzy logic system. If the inputs are outside these ranges, they won't activate any rules. Review your membership functions for each input variable. Make sure they're appropriately defined and cover the entire range of possible input values. It's crucial that for any given input value, at least one membership function has a non-zero degree of membership. Examine the rules in your fuzzy logic system. Each rule should be possible to trigger based on the defined membership functions. If the rules are too restrictive or specific, they may not be activated by your input data. Test your fuzzy